think about those incredibly sharp lines you see in a logo, maybe. Or how a 3D model spins around perfectly, no fuzziness.
Yeah, that crispness, the way it scales. It really all boils down to how computers use numbers, doesn't it? Especially in design.
Exactly. Underneath all those visuals, there's this fundamental language. Data structures that tell the computer how to understand shapes, how to handle space.
That's right. And that's what we're digging into today.
Vector and point data structures. Now, I know it sounds maybe a bit technical, a bit in the weeds.
Maybe a little, but honestly, it's the bedrock. It's under everything from the texture reading to, massive game environments.
So our mission, let's say, for this deep dive is to unpack these ideas, make them clear, engaging. We've got this lecture, some briefing docs in English and Korean.
And we're going to pull the key stuff from all of them, show you why it matters, reveal some surprising bits, even if you're not deep into design yourself.
Okay, let's get into it. We're talking digital representation of design stuff. Two main ways, right? Vector and raster.
Vector first. Think of it like a mathematical recipe, instructions for drawing.
Right, like the lecture said, defining a building by just 4 points, the coordinates of the corners.
Exactly. It's just this neat little package of numbers, but it perfectly describes the geometry. Super efficient.
And then there's raster.
Yeah.
Now, we won't get totally lost in how things get rasterized today.
No. But the basic idea is like a digital photo. It's a grid, right? Tiny squares of color, pixels.
It's like taking a picture. As the lecture mentioned, the camera sensor grabs light, records it as this grid of dots.
And what's really interesting is whether it's the sharp math lines of vector or the pixel grid of raster, it all comes back to numbers for the computer. That's what it works with.
Okay, but here's where it gets really, really interesting for me. Points and vectors. These core concepts, they can be the exact same set of numbers.
Yeah, it's purely about how you interpret them. It's context.
So take 3 numbers. Let's call them X, Y, Z.
Okay.
Those numbers could just pinpoint a location in 3D space, a single spot, a point.
Right, like a star on a map.
Right. Those same 3 numbers, X, Y, Z, could also describe a vector.
Okay. So like an arrow, it has a direction and it has a length pointing from, say, the origin to that location.
Exactly. Same numbers, totally different meaning.
And that difference in interpretation, that's absolutely key. The Korean briefing called it a problem of interpretation, difference in interpretation.
So the raw data itself is just there. It's neutral. It's the framework we apply, the lens we use that gives it purpose.
Precisely. The computer doesn't know if 3, 4, 5 is a dot or an arrow until we tell it what we mean by those numbers in that context.
It's like language, isn't it?
Yeah.
Just letters until you put them together with meaning.
That's a great analogy. And those numbers, those coordinates, they only make sense if we agree on the space they live in.
Which brings us to coordinate systems. You absolutely need them.
Oh, completely. The lecture, the English briefing, they both stress this. Without coordinate system, we cannot interpret, cannot understand the relationships between points, vectors. It's impossible.
They provide the framework, the context, the space, basically.
Yeah. Think about just 2 numbers, 12 and 22.
Okay. Just numbers.
But if I say those are Cartesian coordinates, suddenly, boom, you know exactly where that point is on a 2D grid.
Right. X and Y axis. Standard stuff.
Standard, yeah. And fundamental for CAD, based on those perpendicular axis straight line distance, that's Euclidean distance. That's the main one we use.
But it's not the only one.
Not at all. You've got spherical projections for mapping the Earth, dealing with curves.
Okay, makes sense.
Or even just positioning things on a website.
Yeah.
That uses screen coordinates, often starting from the top left corner.
So those same numbers, 12 and 22, could point to completely different spots depending on whether we're talking CAD or a world map or a web page layout.
Exactly. The system defines the meaning of the location.
So why vectors then? Why are they so central? You said it's about relationships.
Fundamentally, yes. Using vectors lets us measure things, describe relationships between points, how far apart are they, in what direction.
The lecture quote in Korean kind of nailed this, didn't it? About measuring distance.
It did. Although, do, oh, Jenny, G.
Ajaja. Basically, using vectors means you're going to measure distance. It's core to their purpose.
And this whole idea isn't just for drawing lines, is it? You hear vectorization thrown around a lot in other fields.
Oh, absolutely. It's huge in machine learning, AI. You take complex data, represent different features as dimensions in a high-dimensional space.
So each piece of data becomes a point. a vector.
Exactly. And then you can measure the distance between these points to see how similar they are, grouping things that are close together.
But distance itself isn't always straightforward, is it?
Right. We need different ways to measure it depending on what makes sense for the data.
Like the classic straight line.
That's Euclidean distance. Simple, direct.
But then you mentioned others. Cosine similarity.
Yeah, that looks at the angle between vectors. Really useful for comparing text, like articles, to see if they're talking about similar things, even if they use different words. Interesting. And Manhattan distance. Sounds like New York.
Huh. It is. It's like moving in city blocks. Only horizontal or vertical moves allowed.
Right.
No diagonal shortcuts.
Okay, got it. And network distance.
That's like your GPS. Following the actual roads or paths, not cutting straight across buildings. The actual travel distance.
And geodesic lines.
Shortest path on a curved surface. Think airplane routes curving over the globe. Not a straight line on a flat map, but the true shortest path.
Wow. So even something as basic as distance gets interpreted differently depending on the context.
Totally. It highlights how important the right measurement is.
Okay, let's switch gears slightly. This idea of a single point existing in multiple realities. How does that work?
This is where the abstraction gets really cool. A single physical point in your digital model, it can have multiple addresses, depending on the context you're looking at.
The lecture had a great example, right?
Yeah. Imagine a point. In the main 3D world, its coordinates might be, say, 4, 5, 6. That's its global position. But maybe that point also sits on the surface of a curved 3D object.
Right.
Well, that surface has its own 2D coordinate system wrapped onto it, often called UV coordinates. So relative to that surface map, the point might have coordinates like 3, 6.
So same point, different address based on whether you're looking at the whole world or just the surface it's on.
Exactly. And maybe that point also lies along a specific curve running across that surface.
Yeah.
We can define its position along that curve with just one number, a t-value, maybe 0.5, meaning it's halfway along the curve's length.
Wow. So 1 point, 3 different ways to describe its location. 4, 5, 6 in the world, 3, 6 on the surface, and 0.5 along the curve.
Precisely. As the lecture put it, so basically we have 1 point, but this is 1 point, but there are 3 ways of interpreting that information.
And the point itself, it doesn't care about the big picture.
Not really. The lecture made that point. It only knows its local neighborhood, its coordinates within its immediate system, whether that's the curve, the surface, or the world. It doesn't worry about how the surface might be twisting and turning in the larger 3D space.
Like that grain of sand on the beach idea. It only knows the sand next to it, not whether it's on a dune or flat sand.
Perfect analogy. It's all about the local context versus the global one.
Okay, so we have these points, these vectors, defined by numbers, given meaning by coordinate systems. What can we actually do with vectors? What are the basic operations?
Right, so vectors have that direction and magnitude, as the lecture said, direction and, magnitude or intensity. And there are fundamental things we can do.
Like finding its length.
Yep, the magnitude. How long is that arrow? Simple calculation.
And scaling.
Just multiplication. Multiplication is scaling, plain and simple from the lecture. Multiply a vector by 2, it gets twice as long, same direction. Multiply by 0.5, it's half as long.
Like a volume knob for its influence.
Exactly. Then you have the unit vector.
Yeah, the direction only 1.
Right, length of exactly 1. Unit vector is just, we can use the direction without any strong in things need. Basically, pure direction, no magnitude cluttering things up.
And why is that useful?
Because, as the lecture highlighted, so if you use unit vector and scaling together, you can send the geometry in any direction. You take the pure direction,
right,
unit vector, and multiply it by the exact distance you want to move, scaling. Very precise control.
Makes sense. Adding vectors.
That's like, follow arrow A, then from where you end up, follow arrow B. The result is a new arrow from the very start to the very end, combining movements.
And subtraction. You mentioned direction is key there.
Absolutely crucial. Sostabonium. Que uso. Yeah. When subtracting, direction matters. Who you subtract from whom matters. Subtracting vector A from vector B gives you the vector pointing from the tip of A to the tip of B. The order flips the direction.
Okay, got it. Now, dot product and cross product. These sound a bit more math heavy.
They are, but the concepts are super powerful. The dot product takes 2 vectors and gives you back a single number, a scalar.
And that number tells you
about their directional relationship. Just understand that the dot product returns the angle relationship of vectors. Are they pointing in similar directions? Perpendicular. Opposite.
How so?
Positive result means they're generally pointing the same way. 0 means they're perfectly perpendicular. Negative means they're generally pointing opposite ways, like pushing a box, push with it, positive dot product, push sideways, 0, push against it, negative.
Okay, that helps. And the cross product.
Takes two vectors, but this time, what is the return value? A vector comes out. You get a brand new vector.
And what's special about that vector?
It's perpendicular to both of the original input vectors.
Ah, so if you have two vectors lying flat on a table, the cross product points straight up or down.
Exactly. It's fundamental for finding the normal vector of a surface. Which way is it facing? Crucial for lighting, rendering, all sorts of things.
Right, the surface normal, like an arrow sticking straight out from the surface.
Yep. Tells the computer which way is out for that bit of geometry.
So with just these basic tools, adding, scaling, dot, cross product, you can start doing some pretty cool stuff in design.
Oh, definitely. You can calculate precise angles between lines or surfaces using the dot product.
Find the exact midpoint between 2 points.
Easy with vector subtraction and scaling, and interpolation finding points between other points.
Like drawing a line smoothly between A and B.
Yes, that's linear interpolation. Or you can use functions like quadratic curves to create nonlinear curved paths between points. More complex shapes.
Projection, too, like shadows.
Yep, projecting points onto lines or planes uses these operations. And finding the center of a whole bunch of points.
Seems complicated, but the lecture said.
Simple. So, if you add up all the points and divide by the average, you'll get the average. Add all the position vectors, divide by the number of points, boom, center point or centroid.
And even things like realistic reflections and retracing.
Heavily reliant on vector math, particularly reflection vectors, calculated using surface normals and incoming light vectors.
Okay, let's zoom out again.
Yeah.
From individual points and vectors to representing whole spaces. Point grids.
Exactly. It's about discretization. Oh, the whole dian, gorin, oijak, goija o. It's about breaking continuous space down into discrete, manageable points.
So each point in the grid is like a little data container.
Pretty much. It holds information, its location, maybe a color, maybe a temperature, whatever data you associate with that spot in space.
And these grids can be perfectly regular, like graph paper.
They can be uniform grids. Or they can be irregular points clustered together, maybe gaps where you don't need information. You can define complex patterns just by placing points.
And the 3D version is.
Voxels, like 3D pixels, a grid of cubes filling a volume.
So these grids are like a fundamental starting point for loads of design tasks. Site planning, surface detailing.
Absolutely, a way to structure space and information digitally.
And you can introduce forces into these point grids.
Oh, sounds dynamic. It is. You can define things like attractor points. Then, every other point in the grid calculates its distance to the attractor.
And reacts based on that distance.
Right. You can use functions, like the Gaussian bell curve the lecturer mentioned, so the influence isn't just linear. Points really close to the attractor get pulled strongly, points further away less so, creating this nice, smooth fall-off effect.
So points can be pulled towards attractors, pushed away by repulsors.
Or even rotated around a point, maybe based on distance or some other rule. These simple forces, applied across the whole grid, can create really complex, organic-looking patterns and deformations from simple starting points.
It's emergence, almost. Simple rules, complex results.
Exactly. That's a big part of computational design.
Then we get to actually manipulating the geometry we've built. Transformations.
That's basics. Moving things, turning things, resizing things. Translation, rotation, scaling. And projection, squashing 3D down to 2D for the screen.
And these operations work on the points, right? The vertices.
They do. You apply the transformation math to the coordinates of each vertex that defines the shape. Move all the corner points of a cube, the whole cube moves.
But doing that one point at a time sounds slow for complex models.
It would be. That's where matrices come in. Especially 4x4 matrices in graphics.
The matrix math.
Yeah, it lets you combine multiple transformations, say a rotation and a translation and a scale into a single matrix. Then you apply that one matrix to all the points. Super efficient.
And that's why GPUs, graphics cards, are so good at this. They're built for matrix math.
Precisely. Massive parallel processing power crunching those matrix multiplications.
And we need to remember that difference between an object's own coordinate system, its local space,
and the main coordinate system of the whole scene, the world space. Transformations are the bridge. They move objects from their local definition into the shared world.
which ties into planes, doesn't it?
Yeah.
You describe them as local universes.
That's a good way to put it. A plane is essentially its own local 2D coordinate system floating in the 3D world. The Korean briefing said, a plane can be thought of as a standard for a coordinate system. To explain simply, it becomes the origin.
So it's like your personal piece of graph paper within the bigger space.
Exactly. Defined by an origin point where its 0, 0 is, and 3 perpendicular vectors. Its local x-axis, its local y-axis, and the normal vector sticking out of it.
So if I draw a square on that plane, I use the plane's x and y, starting from its origin.
Yep. You're working entirely within that plane's context. It makes positioning and orienting things really intuitive. You want a wall. Create a vertical plane and build on that. Want a floor. Use a horizontal plane.
And you can rotate the plane itself to orient whatever you build on it.
Right. The plane controls the local up, down, left, right. And remember, vectors themselves, unless you attach them to a point, are just directions relative to the main origin. 0, 0, 0. It's placing them within a local coordinate system, like a plane's origin, that gives them a specific location and orientation in the world.
Okay. Now, I can see how someone listening might hear vectors, matrices, coordinate systems, and think, whoa, math overload.
Yeah, it can sound intimidating. The lecture materials actually address that.
What did they say?
Something like math can be scary and difficult, but if you try it, it's quite interesting. If you try it, it's nothing special. That quote came from the Korean briefing. There's often this mental block.
Another quote touched on that too, right? About breaking through.
Yeah, it seems very difficult to break what you have. Once you break it, it's a little easier. It's about pushing past the initial feeling of, this is too complex for me.
And finding ways to make it concrete helps. Like that lucid chart mapping idea from the lecture.
Definitely. Actively connecting the concepts, visualizing them, applying them,
Yeah.
that really cements the understanding and makes it feel less like abstract math and more like a practical tool.
So it really boils down to sticking with it. Perseverance?
I think so. The lecture kind of ended on that note, too, reflecting on just putting in the effort, pushing through challenges. That's how learning happens.
So wrapping up this deep dive, it's really clear just how fundamental these vector and point data structures are. They're not just jargon, they're the bones of digital design.
Absolutely. This invisible mathematical framework is holding up basically everything visual we interact with on screens. It's quite amazing when you think about it.
We really hope, listening to this makes you think about how these ideas might apply in your world. Graphic design, 3D, web stuff, architecture. It's everywhere.
And maybe a final thought to leave you with, now that you've kind of peeked behind the curtain at this foundational layer, what new ways of shaping digital stuff do you see?
Ooh, interesting question.
And thinking about that anecdote from the lecture, the one about the horse and the habit creating those invisible ropes, what habits or assumptions might be influencing your approach to digital design without you realizing it?
And can understanding these fundamentals, the vectors, the points, the systems, actually help you maybe break free from some of those unseen limits, explore new creative ground?
Definitely something to ponder. We really encourage you to keep exploring, maybe even go back to those source materials with a slightly different perspective.